Thank you for joining us for another technical session focused on developing cutting-edge engineering and simulation solutions that help push the boundaries of science and technology. Today, we will focus on a key challenge facing modern hardware electronics: reliability. As electronic systems continue to scale in performance, power density, and complexity, ensuring long-term reliability has become just as critical as achieving peak performance. This is a two-part video series brought to you by the SLAC Center for Simulation and Reliability Engineering. Today's session is structured as follows. We will begin by defining the problem through a review of common failure mechanisms in microelectronics and semiconductor devices. We will then introduce our methodology for addressing reliability throughout the design and development lifecycle. Finally, we will showcase representative case studies and discuss how we ensure that our reliability engineering methods accurately correlate with real-world behavior. Let's get started. Let's first review why reliability engineering is important in the life cycle of microelectronics and semiconductor devices. With continued hardware scaling and rising computational demand, electronic components are exposed to increasingly severe thermal and electrical stresses. Reliability modeling and testing enable us to understand how these stresses can evolve into failures over time. At the same time, the effect of these failures is very important. For example, the financial impact of unplanned downtime in a data center, often reaching millions of dollars per hour, makes reliability a critical business priority. In industries such as aerospace, medical devices, and national infrastructure, failures are not only costly, but can pose serious safety risks. Reliability engineering ensures that these systems meet the stringent performance and safety requirements demanded by their applications. With that context, let's take a closer look at the scope of reliability engineering we are focusing on in this presentation. Reliability engineering is an essential part of the design cycle. It provides an end-to-end framework that transforms performance and lifetime requirements into actionable test items, which then become part of the design validation plan and report, DVP&R. Reliability engineering is driven by structured risk assessment and enables a graded approach to design validation. We use tools such as failure mode and effects analysis, FMEA, to identify and manage risk. Reliability modeling methods, such as fault tree analysis, help reveal reliability bottlenecks and quantify system-level risks. We will review several practical examples to show how FMEA and fault tree modeling supports robust, failure-resistant electronic system design. The importance of a strong feedback loop in the product design cycle is illustrated here. Any issues observed during reliability testing must be fed back into the design process through a structured root cause analysis. The Failure Reporting, Analysis, and Corrective Action System, FRACAS, is the industry standard framework used to document failures, track trends, and identify opportunities for both corrective actions and preventive actions, CAPA. CAPA is a formal structured program that requires proper documentation, traceability, and verification of effectiveness. In many industries, especially medical, aerospace, and other regulated sectors, CAPA activities must also be communicated to the appropriate certification or regulatory agencies. In parallel, a reliability growth program provides a systematic approach for identifying and eliminating failure modes throughout development. By incorporating test results, corrective actions, and design improvements, the program quantitatively measures reliability improvement over time, ensuring that the final product meets performance and lifetime requirements. Now let's dive into a specific example where we walk through three main reliability engineering steps: risk assessment, reliability modeling, and reliability test planning. First, let's focus on risk assessment and examine how it forms the backbone of our reliability engineering approach. FMEA is a widely used risk assessment tool that provides a qualitative measure of risk. The process consists of three major steps: risk identification, risk assessment, and defining action items. The diagram illustrates the typical workflow, beginning with the identification of potential failure modes, evaluating their severity, occurrence, and detectability, and finally translating the resulting risk mitigation strategies into actionable outputs such as updated requirements, quality assurance plans, and other control measures. Design for X, DFX, is a powerful framework for identifying potential failure modes and their root causes early in the design cycle. The X can represent reliability, maintainability, inspectability, safety, manufacturability, and more. Using DFX helps ensure that risks are systematically addressed rather than discovered late in testing or in the field. In power electronics and semiconductor devices, failure mechanisms generally fall into two broad categories: overstress and wear-out. Overstress mechanisms relate to performance under extreme or unintended conditions. Examples include mechanical shock, excessive electrical or thermal loads. Thermal shock: operation beyond maximum allowable temperatures, such as exceeding glass transition temperature, dielectric breakdown, and ESD events. These failures typically occur suddenly when limits are exceeded. Wear-out mechanisms, on the other hand, represent degradation that accumulates damage over time and ultimately limits the lifetime of the device. These include mechanical fatigue, repetitive thermal cycling, electromigration, corrosion, and other progressive damage processes. Being able to distinguish between overstress and wear-out mechanisms is essential when planning design validation. Overstress mechanisms guide performance limit testing, whereas wear-out mechanisms determine lifetime testing, test acceleration evaluation, and qualification strategies. We will take a closer look at several of these mechanisms, how to test for them, and how they integrate into reliability modeling. Now let's move to a critical step in our reliability analysis: reliability modeling. Reliability modeling, such as reliability block diagrams or fault trees, provides a system-level view of how components and subsystems interact, allowing us to identify critical failure pathways and single points of failure. While FMEA is effective for identifying component-level risks, it often cannot capture complex subsystem interactions or cascading failures. For complex systems, this makes reliability modeling a necessary next step beyond traditional FMEA. The objective of reliability modeling is to build a digital twin of the hardware that enables design optimization and comprehensive what-if studies. In this presentation, we focus specifically on fault tree analysis, FTA. The alternative approach, reliability block diagram, RBD modeling, is not covered here. The diagram outlines the major steps in constructing an FTA. We begin by defining the system reliability hierarchy and determining which components should be included in the fault tree. In many cases, FMEA provides valuable input at this stage, helping us prioritize high-risk items as initial contributors and expand the fault tree as additional field failure insights become available. Once the components are selected, we determine how they are reliability-wise connected and assign their corresponding failure modes and causes. Again, using FMEA as a starting point when applicable. FTA is fundamentally a quantitative risk ranking tool, so each failure mode must be associated with an appropriate reliability model to estimate its probability of failure over time. These reliability models, combined with maintenance and spare parts strategies, form the foundation for overall availability analysis. Ultimately, the fault tree results enable us to propose targeted design improvement recommendations and support data-driven decision-making across engineering and operations. Now let's focus on an example and walk through all the steps discussed so far. In this case, we have a PCBA, where the PCB is connected to a component. As shown in the diagram, the FTA is organized into several sub-diagrams, which act as folders that group common components and their associated failure causes. For example, the PCB subdiagram may include vias, traces, and the overall PCB material system. The connector subdiagram may contain brace joints, ball connectors, and other electrical or mechanical interfaces. Finally, the component subdiagram includes all critical components that we have selected for the fault tree analysis based on their risk level and relevance. This structured breakdown allows us to analyze the system systematically and trace how individual failure mechanisms propagate upward to system-level failure modes. We focus on the component subdiagram hereinafter. As shown here, the component subdiagram contains multiple components, each with one or more associated failure causes, connected through standard fault tree logic gates. The OR gate is the most common configuration, representing a series reliability relationship, meaning that the failure of any component will propagate upward and result in the top-level failure event. The reliability and availability of the top-level device can be computed analytically or numerically, provided that accurate reliability and maintainability models have been assigned to each failure cause. In Relia Soft Block Sim, the combined set of these models is referred to as the URD, Universal Reliability Definition, which serves as the foundation for system-level reliability and availability calculations. A reliability model requires accurate failure data in order to produce meaningful predictions. For microelectronics, failure data can be obtained from established published sources such as Military Handbook, 217, Bellcore, and Telcordia databases. However, for new systems or operating conditions that fall outside existing databases, reliability test planning becomes a critical step in generating representative failure data. In this section, we focus on how reliability testing is planned for microelectronics to support model development and validation. To generate failure data within a practical timeframe, we rely on accelerated reliability testing. These tests apply elevated stresses such as temperature, voltage, current, or power cycling to accelerate the dominant failure mechanisms while preserving the underlying physics of failure. The key objective of accelerated testing is not simply to induce failures, but to do so in a controlled way that allows us to extrapolate test results back to normal operating conditions using validated acceleration models. In the next example, we will walk through a transistor reliability test plan and show how test conditions are selected to isolate specific failure mechanisms and extract meaningful lifetime data. First, let's overview reliability testing. Reliability tests can be broadly classified into qualitative and quantitative approaches. Qualitative tests do not aim to prove that the product meets reliability requirements. Instead, they are torture tests designed to uncover hidden failure modes early in the design cycle, so these issues can be eliminated before full production. Examples include highly accelerated lifetime testing, HALT, and other stress-based tests. Quantitative tests on the other hand, are designed to demonstrate product reliability under specific use conditions and environments. For example, a test may aim to show that a product will survive R90C80 conditions for 10 years of use. Quantitative testing also targets infant mortality failures, using methods such as end-of-line testing or highly accelerated stress screening, HASS, to catch units with early defects. Accelerated lifetime testing, ALT, is the main methodology for quantitative reliability testing. It defines a stress-life relationship for the product, either under single-use stress conditions or across multiple stress levels. To illustrate this, we will walk through an example focused on electromigration failure mechanisms, showing the difference between single and multiple stress level ALT approaches. Here we are showing the fault tree of a transistor, highlighting 4 common failure mechanisms: electromigration, thermomechanical fatigue, mechanical and thermal shock, and corrosion. The accompanying pictures illustrate the physical manifestations of these failure mechanisms. We will now walk through reliability test planning and modeling for each of these failure mechanisms. This concludes part 1 of our video series. Please continue to part 2, where we dive into the details of reliability modeling and testing using our transistor example. Thank you for your attention. We hope this session has provided valuable insight into the importance and practical application of reliability engineering in semiconductors and microelectronics.